Good evening, everyone. Welcome to today's problem solving section, week 6, course Applied Accelerated Artificial Intelligence. So, first, the end-to-end accelerated learning, and here we have optimizing the deep learning, the training process. So, here we will see about automatic mixed precision also. So, starting with the deep learning training optimization. It's a optimization algorithm which is used during the training of deep neural network and to achieve the goal, which is like reducing the loss to a minimum. So here we have the two things we can tune, which is like learning rate or weights and other parameters also. So such as even batch size also we can be tuned. So the optimization includes like algorithm includes like gradient descent. So like the optimizers include stochastic gradient descent. Here the idea is like to update the parameter using the gradient of the loss function with respect to the random subset such as mini batch of the data. And if we take say stochastic gradient descent, we have called as update rule. So example is like theta. We update with, so these are like the update rules and the optimization just and if we have the momentum which enhances the stochastic gradient descent by adding a fraction of the previous update to the current one. So this includes like having one more term, we say gamma, adding this term to the loss function. So this helps to accelerate the so stochastic gradient descent in the relevant direction, and if any oscillations are there, it removes that oscillations also. So next we have like RMS prompt, that like is where the it adapts the learning rate for each parameter by dividing a moving average of the recent gradient magnitude, and it's like uh, used in recurrent neural networks. Then we have ADAM optimizer, adaptive moment estimation, which combines the momentum and RMS probe and maintains the exponentially decaying average of the previous gradients and their squares. So this ADAM optimizer is like faster convergence, and it's like uh, commonly used optimizing technique. And in some cases this ADAM optimizer is like having generalization is not that good in some cases. So the next optimizer is ADA grade, uh, which adjusts the learning rate for each parameter based on the historical gradients. And in this, the problem is that learning rate shrinks too much over time. And other variants, we also have Adam W, a variant of Adam with better weight decay handling, and which is also used in training of transformers like GPT or bird models. So sometimes like combination of like SGD plus momentum can also be used for fine tuning the larger models and also for better generalizations. And also learning rate, if we see, learning rate can also be optimized as it is also one of the hyperparameter in the training deep learning models. So how we can optimize learning rate is like one is manually tuning it, trying different values for learning rate, and like hit and trial method or a grid search method, and learning rate schedulers such as step decay, exponential decay can be used. And also like learning rate warm up can be used where we start with a small learning rate and gradually increase it for the first few epochs, and this is useful for training larger models like transformers. And we have like hyperparameter optimizations. Some of the tools include like rate tune, or if we want like automatically find the best learning rate, then we can do grid search or random search or optimization techniques such as Bayesian optimization. And learning rate finder LR range test, which like gradually increase the learning rate during a short training run and plots the loss. So, like this LR, we can use it to choose before the like loss starts to increase rapidly. And next is deep learning training optimization. So here we have three gradient descent based methods. We have stochastic gradient descent. Um, Stochastic is like it picks the data in batches in terms of what randomly using the probability. And there is like mini batch gradient descent, and like big chunks of batches is fed into them for the momentum. And uh, the momentum is used to like reduce the high variance in the stochastic gradient descent. And so to start with, like just let me brief what is the gradient descent. It is like it is a gradient descent is an optimization algorithm used to minimize the loss function. And how it is done? It is done by updating the model parameters in the direction of the steepest descent. And the different types of gradient descent is like batch gradient descent, which is called the vanilla gradient descent, which uses the entire dataset to compute the gradient and update the parameter once per epoch. And the pros, like it is stable convergence and deterministic, but it is very slow for larger dataset and requires larger memory. So when can we use this kind of batch gradient descent is when the dataset is small and which can fit into the memory. So the next is stochastic gradient descent, which is like we uses like one random point to compute the gradient and update the parameter for every single sample. So it is faster and it can escape the local minima due to the randomness. But the disadvantage is it is having high variance and converges less smoothly. So when dataset is large and when speed is important, this is used. The next is mini batch gradient descent. So this is like it works by splitting the dataset into small batches and performs the update per batch. So till now, mini batch is whenever we have say smaller batch, example say 32 or 64 or 128 as the batch size, and we perform the update per batch. So this balances between the speed and the stability. So it's efficient with the GPU acceleration and it has a smooth convergence compared to the SGD. But this requires tuning the batch size. Now here we have another tunable parameter which is batch size. And it is standardly used in all the deep learning such as CNNs, RNNs and transformers. So another thing which we saw is the batch gradient descent, which is the also known as the vanilla gradient descent. So, and once we have covered the stochastic gradient descent, which is like one point, random point in the is used to compute the gradients and update the parameters for every single sample. So the trade-off we have the mini batch gradient descent, which uses the batch size, a mini batch, and then performs the update. So where can we use this batch gradient descent is, say we have very small data set. Next, where can we use this? SGD is we can use in online learning or larger data set, and mini batch can be is commonly used in most of the deep learning applications. So what is this mini batch? I'll just again go little depth. So gradient descent, mini batch gradient descent is an optimization method that updates the model parameter using a small subset of the training data called as batch at each step, rather than using the entire data set or a single data point. So if we have entire data set, it was this batch, and single data point was SGD. So it's in between this two. So instead of calculating the gradient of the loss function on the whole data set, which is like huge or just a single point, we split the data set into small chunks called mini batch and then compute the gradient using one mini batch at a time and update the model parameters. So this process is repeated across all the mini batches in one epoch, and then we go for the next epoch. So this is we understood like mini batch is in between of this two. So why mini batch? So using mini batch speed up the training compared to the full batch gradient descent, because we don't have to wait for the entire data set to be processed before updating the weight, and it is stable stability wise because their update are more stable and less noisy than the SGD, which uses single sample, leading to smoother convergence. And with respect to the hardware utilization, mini batch allows for efficient use of the hardware accelerators such as GPUs or TPUs, which process batch of data in parallel. And the common batch size can be 32, 64, or 128, or even 256. And it depends on the hardware memory and the model which we have. So next is deep learning training optimization. So we have here mixed precision. So what is mixed precision? Mixed precision means using different numerical precisions, like say 16-bit floating point number and 32-bit floating point number during the training to speed up the computation and as well as reduce the memory usage without sacrificing much on the accuracy. So if we are like looking at the memory consumption to accommodate larger DNN models and also the memory bandwidth which will be required to transfer data for this larger model might require large like has larger models requires larger data, so the transfer also needs to be done during the training phase. So to speed up in terms of the computation, um, the some of the advanced optimization techniques to accelerate the GPU uh, is like we have something called accelerator linear algebra or XLA. So this is like a form of TensorFlow, a special compiler. Uh, it is also used in transfer learning. So we will brief about mixed precision next slide. Before that, let's say like how it works with the mixed precision. So the computations are done mostly in say we do it in float 16, say half precision, which is faster and takes lesser memory. And some of the critical parts like loss scaling, weight updates are done in 32 so that we can maintain the numerical stability. And this is supported by GPUs like NVIDIA's TensorFlow. And here we can achieve faster training due to faster math operations and less memory usage. So allowing the larger models or bigger batch sizes. And this is often used in training large transformer models. Next is we have the XLA, Accelerator Linear Algebra. It is a compiler for linear algebra operation developed by Google that optimizes TensorFlow computation and also other computation like JX by fusing operations and generating highly efficient machine code. So how does it work is like it takes the computational graph and compiles them into optimized kernels and then reduces the kernel and launches kernel the overhead which is required by the kernel launch is also reduced and it improves the memory access pattern and enables faster execution for the complex models or complex like some custom operations. So the benefit is like faster runtime for training and inference, better hardware utilization, and can like enable optimization, which is not possible in the regular graphic uh, execution. And the transfer learning is like transfer learning. It's like you reusing a pre-trained model or a part of it on a new but related task. Instead of training a model from scratch, we start with the learned weights and tune or adapt them. So a model is trained on large datasets, say ImageNet for images, or large dataset like NLP model, natural language processing model, which is used as a pre-trained weights as an initialization. So what we do is either we like freeze the earlier layers and only train the last layer on the task, or we fine tune the entire model on the specific dataset. So using the transfer learning, we can save like training time and also we can like work well when we have a limited data for the task and it often achieves better performance than training from scratch. So, so the mixed precision is like we have a lower precision for faster training and less memory. So this speed ups and larger batch size can be used. And next is XLA is like a compile and optimize computation graph, and where it is used is like faster execution, better hardware uses, and we have transfer learning. So it does what is this is it reuses the pre-trained model for new tasks, and where this can be used is like it saves the training time, improve the performance, and on smaller data. So next is mixed precision. So a mixed precision is using different numerical format with respect to the deep learning, like using a single and a half precision for computation during the training of a deep neural network, and like single precision is like 32 bit floating point, and half precision is like float 16 FP16. So the training of a deep neural network, say we use two types of data type precision, so that this is like an high level optimization process, and here like we use the mixed precision. So there is a requirement for the resource, uh, that the usage of this precision, like we need to see how modification in the hardware so that this type of mixed precision can be used. So we consider like GPU architecture, or which facilitate this mixed precision use, which is the first one is the Ampere. So the GPU architecture in the Ampere uses the mixed precision, and next is the Voltas, for like fine tuning architecture and mixed precision, and also Turing. These are which supports the mixed precision. So tensor core, uh, it's like we have multiplication then giving the output, and FP32 tensor float 32. So this FP32 we had some issue with that was overcome in the B float 16 by modifying this number of bits it's given for the precision range, and has like for the B float the dynamic range issue which is there in the FP62 is like overcome. So the dynamic range issue, using the method called scaling, can make like FP62 perform better to, but then we have this B float 16. So the benefits of the mixed precision include like for a math intensive operation using tensor cores, and it requires lesser band like memory bandwidth, and data transfer operations are speed up. So it requires lesser memory, thus the training and deployment of larger uh, deep learning, a larger neural network model is possible, and the speed up achieved is like almost 3x. Next is mixed precision training. So example, we said like mixing the 16-bit floating point and 32-bit floating point arithmetic using a neural network training. So here the goal is to like speed up the training and reduce the memory consumption by maintaining the model accuracy. So say FP16 operation, which is like faster and requires lesser memory than float 32. So the modern GPUs like Tensor cores in the NVIDIA are specially optimized to accelerate the float 16 operation. So using this float 16 for most calculation can speed up the training and allow larger batch size and bigger model. So the weights and activations are stored in the computer, like stored and computed mostly in FP16. And certain operations sensitive to numerical precisions like loss scaling, gradient accumulation can use float 32 to avoid issues like overflow and underflow. And what is loss scaling? Loss scaling is like applied to prevent small gradient values from becoming zero due to limited float 16 precision. So say for example in mixed precision we can use float 16 in forward and backward pass, say for the faster computation and less memory, and model weight say we are storing it in FP32 or 16 depending on the framework. So maintaining the numerical stability and the loss scaling, that is like scale the loss to avoid the gradient underflow. So this way, this is just an example of mixed precision. So this can speed up the training up to like say 1.5x or 3x faster supported by the hardware. And memory efficiency, like we use lesser GPU memory, has like bigger batch size or bigger models can now be used. What is the accuracy? It is comparable results to full FP32 training. So how to preserve the small gradient values during the mixed precision training is done using the loss scaling. So what is loss scaling? When we are using the safe float 16, the I think loss scaling is there. Okay, scaling is required. So what is that? We choose 16 format for the convolution and hyperparameters say FP32. This is another example. And so some of the network becomes network gradient becomes very tiny or zero. So the gradient value required to be shifted to FP16 representable range from FP32 training section. So the solution is like scaling and porting the model. Okay. So we have something called loss scaling. Loss scaling is like when we are using the float 16. The numerical range is much smaller than the float 32. So gradients become very small, close to zero, and FP16 might round them up to zero, and this is called underflowing. So this causes training to fail or because the model never learns from those tiny gradients. So what does this loss scaling do? It is like multiplying the loss value by a large constant factor called the scalar factor before backpropagation. This makes gradient large and prevent underflow in the float 16. After the computation of the gradients are scaled back down by dividing the same factor. So in the process, say we multiply the loss by a scale factor, then perform the back propagation. Gradients are now large, and then we divide the gradients by the same scale factor before applying the optimizer update. So multiplying the loss increases the gradient magnitude, keeping them within the float 16 representable range. So then by scaling the gradients back, the original value are preserved, preventing the loss of small gradient information. And also we have automatic scale scaling. This is a modern framework to handle this loss scaling automatically, which tries a large scale value. And if the gradients overflow, that is, it becomes infinity or not a number, they reduce the scale factor dynamically. And if no overflow occurs, they increase the scale factor to the maximum precision. So here we saw about the loss scaling, which preserves the small gradients in the FP16, and this scaling up prevents the underflow during back propagation. And we perform the scale down operation to restore the original gradient scale after the back propagation. So um, now the gradient is like shifted to float 16. How does we like get the similar accuracy even though like changing to the float 16? So in the mixed precision training, the model weights and activations are often stored in float 16 to speed up the computation and save the memory. So the gradients which are used to update the weights are very small and thus suffer from the precision loss or underflow if stored directly. So to preserve training accuracy, gradients are often computed and accumulated in float 32 or scaled approximately loss scaling when computed in float 16 or stored in float 32 but applied to float 16 weights. So this shifting or casting of gradients between float 32 and 16 helps the numerical stability and accuracy of training even though we are using the lesser precision like float 16. And why this is necessary is that float 16 has limited precision and a smaller range compared to 32. So if the gradients are stored or computed directly in FP16, small gradient values might be lost due to rounding or underflow. So this result will make the model to have like poor convergence in the model or the training instability. So the common approaches to maintain the accuracy is like keeping the master weights in 32. Weights are stored in both 16 and master copy of float 32. Gradients are computed in 32 but converted to 16 and then converted to 32 for optimizer step. This is how like frameworks in NVIDIA or the PyTorch AMP work. So the loss scaling is like multiplying by a large scalar before backward pass to scale gradients up. And this keeps the gradients in a representable range of float 16. And after the backward pass, the gradients are scaled down before updating the weights. So in the PyTorch AMP, in the forward pass, it uses FP16. Gradients are computed in FP16 but internally scaled, and gradients are converted to 32 before optimizer update. The master copy of the weight in 32-bit format is updated, and the 16-bit weights used for forward pass are updated from the master copy. Yeah, so this one we are seeing about the loss scaling. So shifting the gradients to float 16, it's like using the gradients for computation but managing the precision to avoid the loss, and then we store the master or the golden weights of 32-bit and we have the loss scale. Okay, so loss scaling, so as we said, is a technique used in mixed precision training to prevent gradient underflow when using 16-bit floating point numbers. So FP16 has a smaller range and less precision than float 32. So when gradients are very small, they can become zero in FP16, which means the model stops learning properly. To avoid this, we can scale up the loss value by a large number before backpropagation, which makes the gradient larger and less likely to underflow. After computing gradients, we scale them back down before the optimizer updates the weights. So how does this work? Is here we have scale factor, which is multiplied to the loss. Performing the gradient, back propagation to the computed gradients. Now we have a larger value. So divide this gradient by the same scale factor to bring them back to the correct scale. So this is used the scale the gradients to update the weight. Suppose, for example, we have loss say 0.001. Now we multiply with 1000, say 24. So it becomes 1.024. Now compute the gradients using the scaled loss. After the backward pass, divide the gradients by 1024 and then update the model weights with the corrected gradients. So this is the example. And so the modern we have like automatic loss update scaling, which is like modern deep learning frameworks do this automatically with dynamic loss function loss scaling. So they try a larger scale factor initially, and if the gradients becomes not a number or an infinity, they reduce the scale factor. And if they see no overflow, so the next step they increase the scale to maximum precision. So what is the benefits of this? This prevents smaller gradients from becoming zero in float 16 and enables stable and accurate training with maximum precision, improves training speed and reduces memory usage. So what are the steps? The first step is that we multiply the scale factor. Next is we compute the gradients, back propagation, and then next is we unscale it, like divide by the scale factor, and then is the update model weights. So small gradients means in the gradients value which are close to zero but still representable in the numerical format. So these small gradients might be meaningful but just tiny in magnitude. So there's no guarantee that they cause problem in training by themselves. So this is like what is gradient underflow. This happens when the training becomes so um, during the training the gradients becomes so small that they cannot be represented properly in the number format due to limited precision and range. Say for float 16, we have very small range get so this get rounded to zero. So this is numerical issue which is also called as like which is causing the loss of the gradient information. Underflow effectively means the gradient is zeroed out, which prevents learning. So I'm just trying to differentiate between two terms, small gradient and gradient underflow, because we are using these two terms. So gradient underflow means gradient is too small to be represented and therefore it becomes zero. And what is the it causes is that it stops learning because of the gradient lost. Whereas small gradient is like tiny but still representable and training still proceeds normally. And why we have underflow, like say in float 16, there is a limited precision. Small gradients can underflow and become zero. Loss scaling helps avoid this by scaling up the gradients before backpropagation. Yeah. So choose the 16 format forward pass, scale the loss and back propagation of the scaled gradients, and then unscale and optimizer will perform the weight update. Next is automatic precision, mixed precision. So this AMP stands for automatic mixed precision. So it's a technique and a set of tools or framework features that automatically enables mixed precision training by managing when and where to use float 16 and 32 precision in our model. So without requiring to manually change the code. Why to use AAMP? It's like it has to speed up the training and reduce the GPU memory usage by using the float 16 wherever possible, and maintains the numerical stability by keeping critical operations in float 16, and it handles the loss scaling automatically to prevent gradient underflow, and this simplifies the process of applying mixed precision training. So the implementation, common or popular implementation by PyTorch includes torch.cuda.amp module, which is introduced from Python PyTorch 1.6 plus, and TensorFlow Mixed Precision API, tf.keras.mixedprecision. Say for the mixed precision from PyTorch, torch.coda.amp, or from the TensorFlow tf.keras.mixedprecision. So these are the two. Next is how we can see is that, so one of the example code for PyTorch may be like torch from torch.cuda.amp. We can import that autocast and grad scalar, and we can initialize a scalar which is equal to the grad scalar, and from the data and the target in the data loader we can optimize. So by using optimizer.zeroGrade, and then using the autocast, and the output of the is equal to the model updater, and can have the loss function there. After this, we can have the scalar dot scale loss dot backward, and then scalar dot step optimizer, and scalar dot update. So some basic example here using the PyTorch. So AutoCast, this enables a mixed precision operation automatically, and grad scalar, this one handles the loss scaling. So what is the benefit of this? It is faster training, less memory, and stable training. And the purpose is to simplify and optimize mixed precision training. Next is AMP uses. So one of the uses, like it can speed up the training. So AMP leverages the float 16 half precision operation wherever it is possible, and float 16 computations are faster, have supported hardware includes NVIDIA's GPU with sensor cores, and this reduces overall training time. To reduce the GPU memory usage, like float 16 enables half precision, so which can allow now larger batch size or bigger models to fit into the GPU. And to maintain the model accuracy and stability, this AMD automatically keeps sensitive operations in float 32 to avoid numerical instability and uses the loss scaling to prevent the small gradient values from underflying. This means like uh, we get a mixed precision speed ups without sacrificing the model accuracy. And the AMP abstracts many manual castings between 32 and float 32 and float 16. So developer can just like add few lines like autocast and auto scalar to enable mixed precision. And this reduces the complexity and potential works in the precision handling. So when it comes to the hardware utilization, so this makes use of the specialized hardware like tensor cores on NVIDIA GPU and improves its throughput and energy. So AMP is widely used in the training, state-of-the-art models like large transformers, CNN, etc., to improve the efficiency without losing the accuracy. So we are here, we are trying to reduce the time to train the models and like faster training, and then memory efficiency is achieved like training the larger models, or now we can, as the memory efficiency is low, we can increase the model size and also batch size. Accuracy or preservation like stable training with float 16 precision. Ease of use like simple API reduces the developer effort. Hardware optimization which leverages like GPU tensor cores for better performance. Next, we will see about the transfer learning. So, transfer learning is like a process of using the learned features from a pre-trained model to train new data. So, transfer learning is a technique in machine learning. There, we can take a model trained on one task and reuse it fully or partially for different or related tasks. So training a deep learning model from scratch, we require a lot of data and computation power. So many problems share common features, example edge shapes in the image, etc. So transfer learning leverages this knowledge learned from the large data set task to improve the performance of a similar or different dataset or task. So we use the pre-trained model already tuned on larger dataset like ImageNet for images or say BERT for NLP and reuse the features. So this early layers of the pre-trained model usually learn general features useful across many tasks. So we perform like fine tuning, which freezes some of the layers, usually the early ones, to keep the learned features and retrain or fine tune the last layers on a specific data set or task. So the fine tuning the entire model, if we consider, with or like we can fine tune the entire model with a smaller learning rate. So example, we can have a resonant model trained on an image net, say to classify medical images. Now say we are using the BERT pre-trained on large test for sentiment analysis on a movie review. Next, say using a object detection model for custom detection task. So what is the benefit here is that we have lesser training time and lesser data required for the newer task, and this often leads to better accuracy with smaller data set. So why to use the like transfer learning? This saves time and computation. So training learning models from scratch can take, let's say, several days or weeks and require huge computational resources. So transfer learning allows to start with a model that's already learned useful features, so can fine tune it. This drastically reduces the training time and computation cost. So this works well with smaller data set. So say when many real world problems have limited labeled data, like which makes training from scratch difficult. So here the transfer learning knowledge from the larger data set to boost performance on small data set is used, and it helps model generalize better when we don't have tons of data. So this is like transfer learning. Okay. So now we said why we need transfer learning is when we have a smaller data set, that is like in the real world problems when we have limited label data, so where their training from scratch gets difficult. And the transfer learning uh, boosts the performance of the model on small data set by using the knowledge from the larger data set, available larger data set. So it also helps the model to generalize better when compared to, like, when we don't have much data. So better performance. Next, it leverages the domain knowledge. So earlier layers in the neural network, which often learns like genetic features like edges, textures for images, say grammar, patterns for text. Transfer learning reuses these general features and focuses on learning specific task, like task specific features. So, and also this enables faster prototyping. So, like we can quickly experiment with larger tasks by adopting pre-trained models. And for this is help for the startups or research, like where rapid prototyping is required. So now, for example, I just describe if I have a ResNet and a custom dataset. Now we want to perform transfer learning. So we import the libraries and load the pre-trained model. And now we can replace the final layer for, say, assuming 5 classes, we can replace that layer with the number of classes we want. Then we will freeze the earlier layers. So freeze means some of the layers which we want to keep it as it is, pre-trained weight fixed. and we load the data set and define the optimizer and loss function and train the other weights. So the pre-trained ResNet learned general images feature from ImageNet. So now we replace the last layer for 5 class classification and we freeze the weights in the initial layer, and last of the few other layers from the end we have made it to learn for the new data. So this is the fine tuning of the model, and this is like we can perform quickly, so without training from the scratch. So next in the transfer learning with NV, okay. So this can be for the image classification, object detection, segmentation, or with respect to automated speech recognition or NLP, natural language processing. So next is transfer learning with NVIDIA's N8O. So N, sorry, TAO stands for Train, Adapt, Optimize. So this NVIDIA's TAO, Train, Adapt, Optimize toolkit is like no code, low code. This is like no code or low-code AI toolkit designed to simplify and accelerate deep learning model development, especially for NVIDIA GPU platform. And it's ideal for transfer learning and fine-tuning pre-trained models on the custom dataset. So, why we want to use TAO toolkit for transfer learning? It provides a pre-trained AI model for tasks like image classification, object detection, NLP, speech recognition, etc. And this enables transfer learning with our own dataset without expensive coding. And next, it automates the training, proning, quantization, and development, and optimizes for NVIDIA GPU and Jetson platform. And this helps to build custom AI model faster and more efficiently. So how does this transfer learning is performed with the TAO toolkit? Here is like first we select the pre-trained model from the TAO models do like ResNet, BERT or SST, and then we prepare the dataset in the required format. So next we use this TAO toolkit command line interface CLI or the GUI to adapt, fine tune the model parameters, the pre-trained model to the dataset, to our own dataset, custom dataset, and then train the model using the our dataset, and then optimize the model if required, such as coding or quantization. So this is used to like to deploy the model on NVIDIA GPU or edge devices. So, so for installing the TAO toolkit, one option is like we can use NVIDIA NGC containers and use Docker pull and download the pre-trained model, and then use this pre-trained model uh, and the data set, and then the fine tuning of the pre-trained model. So, so what is the advantage of this TAO toolkit? It is like now we require minimal coding and we have a built-in support for multiple AI tasks and the automated training pipeline for training, optimization, and deployment. So this and also the leverages the NVIDIA hardware acceleration. Okay, so what is this NVIDIA TAO? It's a toolkit developed by NVIDIA. So what is the workflow with the TAAO? We choose the pre-trained model. So first step is the uh, pre-trained model. Then we prepare the custom data set. Then we use the toolkit for fine tuning. This means adapting the model, fine tuning to adapt the model. Then optimize that, and finally we can deploy this model. So we can export and deploy this model. Sorry. So next is the computer vision flow. So this AI models can be commonly used in computer vision tasks like post estimation, license plate detection and recognition, PeopleNet, facial landmarks estimation. Next is the transfer learning image classification with VGG16. So this is like very deep convolution networks for larger scale image recognition. So this we know ResNet 16. We have this skip connection and this one the image lecture. These are like some of the data set and specification for classification. We have two files, specification files, uh, the retrain spec and the classification spec, and the classification. The specification file consists of three components: model, train, and evaluation configuration. So yes, with this we go to the previous year assignment questions. So why is the law scaling used in the mixed precision training? Yes, what will be the answer? Why is law scaling used in mixed precision training? So why is the loss scaling used in the mixed precision training? Answers. We have seen that it is used to prevent the like preserve the small gradient values. So in the mixed precision trainings, they both 16-bit float 16 and 32-bit FP32 floating point types are used to speed up the training and reduce the memory usage. But however, in the float 16, we have a limited dynamic range, which can cause very large gradients to very small gradients to underflow to zero. So small gradients to underflow to zero. Effectively, this will be like this smaller gradients will disappear during the brand propagation. So loss scaling is a technique used to prevent this. And what is the loss scaling? It multiplies the loss by a large constant called the loss scale before backpropagation. This makes the gradient larger in magnitude, reducing the chances of underflow in float system. After computing the gradients, they are divided by the same scale to bring them back to the correct value, scale value before the optimizer step. So why this option is correct? I hope you understood. So next, to increase the learning rate for faster convergence, so loss scaling does not change the learning rate. Next is to reduce memory usage for larger batch sizes. The mixed precision helps with memory, but the loss scaling uh, does not specifically perform anything with respect to memory. To improve regularization in deep neural network, loss scaling does not act as a regularization. So, what is the correct option? So the loss scaling is used in mixed precision training to prevent small gradients from underflowing to zero by preserving their magnitude during computation. Okay, next question. Which of the following is not an optimizer? What is this SGD? So which of the following is not an optimizer? Yes, softmax. So here this Adam SGD is stochastic gradient descent and this ADA grade, these three are all optimizers. And used in the training neural networks. So they update the model's weight based on the gradients computed during the backpropagation. Whereas the softmax is on the other hand, it is not the uh, optimizer. It is another activation function. So it's not an optimizer, it is an activation function. Commonly used in the output layer of the classification model to convert logits or the raw prediction scores into probability. So if we have say linet 5, this output say trained on MS dataset, then it will have 10 outputs 0 to 9, 10 class classification problem, and this value is called logits, which is applied through softmax to get the probabilities. So the ADAM is an adaptive optimizer that combines momentum and adaptive learning rates. And whereas SGD is a basic optimizer that updates weights using the gradient of the loss. And adapt rate optimizer adapts the learning rate for each parameter based on the past gradients. Softmax is an activation function that outputs a probability distribution over the class. So softmax is not an optimizer, it is an activation. So next question, which of the following statement is or are not a benefit of mixed precision? Yes. So the first is the speed up math intensive operation using tensor cores. Uh, the next is the requires less memory bandwidth, thus data transfer operations are speed up. And next is requires less memory, thus the training and deployment of larger networks are possible because 16-bit now, so we can deploy some more larger models or larger pixels. So the answer is none of the above, as all the three statements are benefits of the mixed precision training. So speed up math intensive operation using tensor core is true because mixed precision allows deep learning models to use specialized hardware units like tensor cores of NVIDIA, which are optimized for float 16 operation, significantly improving computational speed for matrix multiplication and other math heavy tasks. And next, it requires lesser memory bandwidth, thus data transfer operations are speed up. This is also true because float 16 uses half the size of the float 32, meaning the lesser data needs to be transferred between memory and computer node. So this reduces the memory bandwidth usage and speed up the data movement, which can be bottleneck in training and requires less memory, thus the training and deployment of larger model networks are possible. This is also true since float 16 value takes up less space, GPU memory usage is reduced, enabling training with larger models or bigger batch size on the same hardware. So all the three are correct. Next question. Which of the following optimizer is best suited for to train on sparse data? So what's the answer? See? Okay, so the correct answer is grade, which is also called as adaptive gradient algorithm. So this is like particularly well suited for sparse data, that is data set with many zero values such as text or recommendation system, because it adjusts it adjusts or adapts the learning rate for every uh, like each and every parameter individually. So because of this, it works well for the sparse data set. That is like it increases the learning rate efficiency for infrequently occurring features by assuming them larger learning rate. Frequently occurring features get smaller update, preventing them from dominating the learning. So this is especially useful in applications like natural language processing, NLP, or recommendation system, or like in the click-through rate prediction. And why the others are not is like mini batch gradient descent. This is a training strategy, not an optimizer. So it splits the data set into small batches, but doesn't adapt to sparsity. Next, this accelerated gradient is a momentum-based optimizer, improves the convergence speed but doesn't specifically handle sparsity. Next is the gradient descent, which is the vanilla. So it's plain, that is called vanilla. So vanilla gradient descent, or the gradient descent uses a fixed learning rate for all parameter and does not adapt to sparse data set characteristics. So this is why the adaptive gradient algorithm, AdaGrade, is designed to handle the sparse data efficiently by adapting the learning rate per feature, making it most appropriate choice among the for the sparse dataset. So I hope like what this AdaGrade does is it it increases the uh, training efficiency by like if we have a very infrequent occurring features, for them it assigns larger learning rate so that those features will have import given some importance, like good importance, whereas now when the features which are occurring frequently, they are given smaller updates so that we can prevent them from dominating the learning. The answer is next question. What does TAO stands for? So T stands for train, A stands for adapt, and O stands for optimize. Option C. Train, adapt, optimize. So this is like, so the TAO stands for train, adapt, optimize. This is a common framework used in machine learning and in the NVIDIA's TAO toolkit. So the train, we start a pre-trained model and train it on a new dataset. Adapt is like fine-tuning or adapt the model to specific task or domain from transfer learning. Optimize, optimize the trained model for deployment, such as pruning, quantization, or converting to tensor RT for inference. So finally, what is TAO? It stands for train, adapt, and widely used for simplifying and accelerating the process of building production-ready AI models. The next question is, transfer learning is a process of using. So the correct answer is answers option A. Learned features from a pre-trained model to train a new data. So transfer learning is a technique in machine learning where model developed for one task is reused as the starting point for a model on a second task. So it leverages the learned features or the knowledge from the pre-trained model, typically trained on a large data set like ImageNet, and applies it to a new data set or a task, often with much less data. So the learned features are the pre-trained model which has already learned useful patterns such as edge, shapes, or language structure. From the pre-trained model is the base model which is already trained on a large data set. And where we apply, so we use this, we apply this knowledge to a new task or a data set, different class or domain. So the correct answer is reuse the learned features from a pre-trained model to efficiently train on a new data. Next question, which of the following best describes the correct order of phases in NVIDIA TAO for image classification? Okay, correct answer is input data structure, spec file configuration, then the training model, then evaluating the model, next prone the model, next retrain the model and test, and then run the inference. So, so what is the steps to build the this model from this NVIDIA's NTAO, TAO for image classification is like first we prepare the data. Then we configure how the model will be trained and train that on it. Then evaluate the performance. Then we perform the optimization such as pruning. Then fine tuning and re-evaluation, and then deploy the model. So the accepted answer is input data structure, spec file configuration, training model, evaluating the model, pruning the model, retrain model and test and run the. So what is input data structure? So it's like involves organizing and preparing the data set, and we need the data in the right format, like images, labels, or annotation, before doing anything else. Like the TAO expects data structure in a certain way for training and evaluation. The next is the specs file configuration. So this involves like creating configuration files like spec files that tells NAO how to train the model. So this spec includes path to the data model architecture and details, hyperparameters, batch size, learning rate, etc. Without this, the toolkit doesn't know how to proceed. So next is the training model. So here the prepared data and specs are used to train the model. Next is training is where the model learns from the data, which is the core step where the weights gets adjusted. Next, evaluate the model. So the testing the model on validation or test data to measure the accuracy, precision, recall, etc. So we want to check how well the model is performing before making any optimization. So next we perform the model optimization, that is reducing the model size by removing less important weights and connection. So next, so this pruning makes the model smaller and faster without a big hit on the accuracy. Um, so we do this after initial training and evaluation to optimize the model. Next is retraining the model and testing it. So the fine-tuning the pruned model to recover any lost accuracy, then evaluating it again. And pruning can sometimes modify the accuracy, so retraining helps the model regain the performance. Then running the inference. So this is using the final trained and optimized model to make predictions on the new unseen data new or the unseen data. So why it is done? The inference is the deployment phase, where the model is actually used in the real application. So the flow is that we start with the model good data, configure the training properly, train and check how well the model learns, then optimize the model to be efficient, such as using the techniques such as pruning. Next, fix any accuracy drop with retraining. Then finally deploy the model for real use. Okay, next question. How many? So the correct answer is this one. Going to the next question. How many bits are used to prevent? To represent the exponent field of B16. So B float 16 is one second. Brain floating point format. So this uses 1 bit sign and then 8-bit exponent, then 7-bit mantissa. So this is the format of the B float 16, which is the brain floating point. And this is different from IEEE 16 float 16, which uses 5-bit exponent. So this is 8-bit. So B float 16 is designed to have the same exponent range as float 32, which has on 8-bit exponent, allowing it to represent very large and very small numbers, but with less precision because of fewer mantissa. So B float 16 uses an 8-bit exponent field. So next question. Which is the best optimizer for training neural networks in less time and more efficiently? Yes, the answer is Adam optimizer. So why Adam optimizer? Adam optimizer is like the adaptive learning rate. Adam adjusts the learning rate individually for each parameter, which helps the model coverage faster. And it combines the momentum and RMS probe ideas. So this allows it to navigate the loss landscape more efficiently and works well. Like it requires less manual tuning compared to others and is widely used as in the most of the deep learning application use Adam as the default optimizer for faster and more stable training. So what are the other optimizers like other training with such as mini batch gradient descent is a training strategy and not an optimizer. Okay, I think this question we have. And this is also improves upon standard momentum but usually doesn't outperform the Adam in efficiency. This is vanilla gradient descent, which is simple but can be slow and less efficient, especially for larger complex. So Adam is the next question. Mixed precision is the is to combine use of. Yes, option A. Yes, it is FP32 and FP16. So FP32 for the parts of the model that requires higher precision like accumulation of gradients, and FP16 for the bulk of the computation to speed up training and reduce memory usage. So this combination balances speed as well as the numerical stability. And float 64 is mainly like used for scientific computing but is rarely used in deep learning due to its heavy computational cost. And FP8 is an emerging format but not widely adapted yet for the mixed precision training. So the mixed precision training is combining the FP32 and FP16 to optimize performance and resources. So any doubts?
Ma'am, where can we get the recording for the videos? I mean, like what you are teaching.
It is provided in this some Excel sheet is shared with you, I think. This Excel sheet. Once again. Yeah, this Excel sheet.
Okay, I'll check. I don't think this has been shared. I'll check.
Yes.
Thank you, ma'am.
Yes, thank you. So here in this announcement, there is a link for the recording sheet, which has access to the YouTube link as well as the Drive link, where like I have uploaded the that week's PDF notes. That is, thank you so much for joining. I'll end today's session.